Alrighty, two topics for today. One is that velocity is relative, and what that means is that it totally depends on your observer as to what the velocity looks like. I've included a link for today's lesson to a really good video where a gentleman who calls himself Professor Dave actually does a really good explanation of how velocity is relative, so I really want to encourage you to watch that. The velocity refers to both magnitude and direction, so obviously that's going to depend on how you're observing it, especially if it's looking like direction. He mentions that relative velocity is the velocity of what is observed minus the velocity of the observer. He doesn't actually put it in equation form for you, but this is really what that is. So you may want to take this particular equation here and write that on your note card. Now, in the example problem that he does for you, he has a car and a truck moving in opposite directions. He has one moving 56 miles per hour this direction, and then he has the truck moving in 45 miles per hour in the opposite direction. Hopefully you can see from that particular example problem just why head-on collisions are so dangerous. It's because you actually are going to add the velocities together, or this, and to get a relative velocity that's often twice as fast as what one particular car is going, and that's why, again, head-on crashes tend to be so dangerous. But I want to take this same car and truck, and now I want to have them going in the same direction. What does that do to the relative velocity? Well, let's say that I'm looking at the driver of the car. What does the car observe? Because obviously he's going faster, so he's going to come up and he's going to pass this truck. What is it going to look like for him? Well, to him, they're going the same direction. So what he observes is a truck that's going 45 miles per hour, and he's going to subtract his speed of 56 miles per hour. And so when you do that, you're going to end up with a negative 11 miles per hour. Well, why is it negative? Well, if you think of yourself in this car as you're passing another vehicle, like if you're in two separate lanes on the interstate, when you pass another vehicle, if you just look out the side window, does it not look like this truck is going backwards? And that's what this negative sign means. To this car, this truck appears that he is going backwards. And so that's why it's negative. Now, if I look at the driver of the truck, what he is observing is the car, so that one goes first, 56 miles per hour, and he's going to subtract his own speed, which is 45 miles per hour, and that's going to give me a positive 11 miles per hour. Again, if you are sitting in the truck and a car passes you, it appears that they're going in the forward direction, but it doesn't seem like they're going nearly as fast as you perceive yourself to be. Maybe if you're looking out the other side, you see all the trees flying by. So they look like they're going much slower than they're actually going, but that's because you're both going the same direction. So to the person in the car, the truck appears to be going backwards. To the person in the truck, the car appears to be going forwards based on their relative speeds. So I wanted to make sure that we actually flipped that example around and did it the other way, so that you could get an idea of what that looks like as well. The other topic we're going to hit today is acceleration. And if we go back to our chart that we started earlier in the module, we said that scalar quantities were distance, time, and speed, and vector quantities were displacement and velocity, and we're going to add acceleration to the vector side of that. What you should be noticing here also is that because velocity is displacement over time, since velocity includes another vector quantity, it itself will be a vector quantity. Acceleration is defined as the change in velocity over the change in time, and since velocity is a vector quantity, then acceleration must be a vector quantity as well. So when you write an acceleration, you also need to be very sure that you're including a direction in that. Okay, but here I have a new concept here, change in velocity. Change in velocity, I always have to take the final velocity, which I'm going to abbreviate with a v sub f, and I'm going to subtract my initial velocity, and I'll put that over my change in time. You want to be very careful not to get these two backwards, because if you get them backwards, you can end up with an acceleration having the wrong positive or negative sign on it, and then you're not going to be able to tell if your object is speeding up or slowing down. Now, in our everyday language, when we talk about acceleration, normally we think of objects speeding up. We even call the gas pedal in our cars the accelerator. When we push on it, we go faster. But in physics, acceleration simply means a change in velocity. It does not necessarily mean we're speeding up. It could also mean that we're slowing down. And so the positive and negative signs on that acceleration are going to be our clue to tell us whether the object we're looking at is speeding up or slowing down. If you look at example 1.6 in your book, I want to look at that not because the calculations are difficult, but because I want to make sure you understand the units that are being used for acceleration. It says that a car is moving with a velocity of 25 meters per second to the east. Notice the direction has been given with the velocity. The driver suddenly sees a deer in the middle of the road and slams on the brakes. The car comes to a halt in 2.1 seconds. What was the car's acceleration? Okay, so you'll notice that I kind of took the equation for change in velocity and I combined it together with the one for acceleration. So when you write that on your card, you may want to write this whole thing down so that you have this piece included in your acceleration formula. So if I look at the information that they've given me, what you have is you have this car and he sees a deer up ahead. There's his antlers. And he's coming along here, and when he gets to this point, he wants to stop so that he doesn't hit the deer. So he's going this direction. When he starts out, he is going at 25 meters per second. The whole idea is that he gets stopped before he hits the deer, so he wants to be at 0 meters per second when he gets right here. Okay? So if I am calculating acceleration, his final velocity is going to be 0. This is what it is at the end. And so I'm going to start with 0 meters per second, and I'm going to subtract his initial velocity, what he started at, which is 25 meters per second. And the amount of time it took him to do that was 2.1 seconds. So if I go ahead and divide this out, I'm going to have negative 25 meters per second over 2.1 seconds. And so that means that my acceleration then is going to be a negative 12 meters per second squared. What does meters per second squared mean? How can you have a squared second? I mean, you can probably understand it. You can have a squared meter or a squared centimeter because that would be area. But how do you have a second squared? Well, what that means is this. When you start your stopwatch at t equals 0, this car is going 25 meters per second, okay? He slams on the brakes. He's trying to avoid hitting the deer. So 1 second after he slams on the brakes, he has decreased his speed by 12 meters per second. So at the first second, he's now down to 13 meters per second. At the end of the second, he's going to decrease this by another 12 meters per second. So now he's down to 1 meter per second. And you notice we said that it took him 2.1 seconds to stop. So that additional tenth of a second is going to enable him to get all the way down to a final velocity of 0. Okay, so that's why it's meters per second, because he decreases it by 25 meters per second for every second. Meters per second per second. is what that actually means. So that's why it's second squared, because it's meters per second for every second that passes, okay? So I want you to notice that this acceleration came up negative. And this is what I was talking about, where we view acceleration as always speeding up, but in physics it's not that way. If his velocity was a positive 25 meters per second and his acceleration was negative, what that means is that the object is slowing down, and it means that his acceleration is in the opposite direction of his velocity. So if his velocity was initially 25 meters per second to the east, then that means that his acceleration is 12 meters per second squared, to the west. It is in the opposite direction of the acceleration, okay? So that's a couple of points you need to make sure you get. If acceleration and velocity have opposite signs, the acceleration is in the opposite direction of the velocity, and the object is slowing down. Now, on the other hand, if the acceleration and velocity have the same signs, then the acceleration is in the same direction as the velocity, and your object is going to be speeding up. Okay, so the signs on these are really, really crucial to figure out what is happening to the object that you're talking about. And that sign is not going to be correct if you don't make sure that you put them into your formula as far as final and initial velocities when you go to calculate acceleration in the first place. So as you're walking your way through those problems, make sure you watch those two things really closely.